Langchain Astra DB Document Loaders. Description: explain in detail. The Langchain Astra DB Document Loaders are a collection of tools designed to efficiently load data from Astra DB, a fully managed, serverless database service by DataStax, into Langchain for processing. These loaders enable you to access and process data stored in Astra DB directly within your Langchain applications, facilitating seamless integration with your data sources. Inputs. Input 1. Explain in detail Astra DB connection details. Credentials, key space, table name. Input 2. Explain in detail query to filter the data to be loaded. Optional. Outputs. Output 1. Explain in detail a list of documents, each containing the data from a single row in the Astra DB table. Output 2. Explain in detail a dictionary containing metadata about the loaded documents, such as the total number of documents and the query used to retrieve them. Steps. Step 1. Explain in detail. Establish a connection to the Astra DB instance using the provided connection details. Step 2. Explain in detail. Execute the provided query, if any, to filter the data to be loaded. Step 3. Explain in detail. Retrieve the data from the Astra DB table and format it into a list of documents suitable for Langchain processing. Metrics. Metric 1. Explain in detail document count, the total number of documents loaded from Astra DB. Metric 2. Explain in detail load time, the time it took to establish the connection and retrieve the data from Astra DB. Visualization plots. Visualization plot 1. Explain in detail none. Visualization plot 2. Explain in detail none. Fine-tune parameters. Parameter 1. Explain in detail none. Parameter 2. Explain in detail none. Uncertainty methods. Uncertainty method 1. Explain in detail none. Uncertainty method 2. Explain in detail none. Challenges and fixes. Challenge 1. Explain in detail. Incorrect connection details or permissions may prevent the loader from connecting to Astra DB. Sample use case that resulted in challenge 1. The provided credentials might be incorrect, or the user might not have sufficient permissions to access the specified key space or table. Fixes to challenge 1. Verify the connection details, credentials, key space, table name, and ensure they are correct and that the user has the necessary permissions. Challenge 2. Explain in detail the query provided might be invalid or might not retrieve the desired data from Astra DB. Sample use case that resulted in challenge 2. A syntax error in the query or an incorrect table name could lead to data retrieval issues. Fixes to challenge 2. Ensure the query is syntactically correct and that the table names and column names used in the query match those in Astra DB. Langchain Astra DB Document Loaders. Astra DB Loader. Description. Explain in detail. The Astra DB Loader is a Langchain document loader specifically designed for loading documents stored in Astra DB. It allows you to access and process data stored in Astra DB for use in Langchain applications, such as building conversational AI models or performing document summarization. Inputs. Input 1. Explain in detail Astra DB client. This input is an instance of the Astra DB Python client, providing access to the Astra DB database. It is used to execute queries against the Astra DB database to fetch documents. Input 2. Explain in detail query. This input is an optional SQL query string used to filter the documents retrieved from Astra DB. If no query is provided, all documents from the specified table are loaded. Input 3. Explain in detail table name. This input specifies the name of the table in Astra DB that contains the documents you want to load. Outputs. Output 1. Explain in detail documents. This output is a list of document objects representing the retrieved documents from Astra DB. Each document object contains the content of the document and metadata, including the document's ID and source. Steps. Step 1. Explain in detail. The loader establishes a connection to the Astra DB database using the provided Astra DB client. Step 2. Explain in detail. The loader constructs an appropriate SQL query based on the provided query and table name. This query is used to fetch data from the specified table in Astra DB. Step 3. Explain in detail. The loader executes the SQL query against the Astra DB database using the established connection. Step 4. Explain in detail. The loader processes the retrieved data, extracting the document content and metadata. Step 5. Explain in detail. The loader creates a list of document objects, each containing the document content and its associated metadata. Step 6. Explain in detail. The loader returns the list of document objects, making them available for use in downstream Langchain applications. Metrics. Metric 1. Explain in detail loading time. This metric tracks the time taken to load documents from Astra DB. It can be used to assess the efficiency of the loader. Metric 2. Explain in detail document count. This metric measures the number of documents successfully retrieved from Astra DB. It helps to understand the scale of the loaded data. Visualization plots. Visualization plot 1. Explain in detail. A histogram of loading time can be visualized to understand the distribution of loading times for different documents. This can identify potential performance bottlenecks. Visualization plot 2. Explain in detail. A scatter plot of document count versus loading time can be created to analyze the relationship between the number of documents loaded and the time required. This can provide insights into the scalability of the loader. Fine-tune parameters. Parameter 1. Explain in detail Astra DB client. This parameter allows you to customize the Astra DB client used for connecting to the database. You can configure connection settings, such as the database name, username, and password. Parameter 2. Explain in detail query. This parameter allows you to provide a custom SQL query to filter the documents retrieved from Astra DB. You can use this to specify conditions, such as selecting documents from a specific date range or based on certain keywords. Parameter 3. Explain in detail table name. This parameter lets you specify the name of the table in Astra DB that contains the documents you want to load. Uncertainty methods. Uncertainty method 1. Explain in detail now. This loader does not involve any uncertainty estimation or probabilistic modeling, so there are no uncertainty methods. Challenges and fixes. Challenge 1. Explain in detail slow loading times. If the Astra DB database is large or the query is complex, the document loading process might take a significant amount of time. You might experience slow loading times if your database contains millions of documents or if you are performing a complex query that requires extensive database operations. Consider optimizing your Astra DB query for efficiency, using indexes if applicable, and potentially using a dedicated database instance for higher performance. Challenge 2. Explain in detail connection errors. If there are issues connecting to the Astra DB database, the loader will fail to fetch documents. You might encounter connection errors if the database server is down, your network connection is unstable, or the provided credentials are incorrect. Ensure the Astra DB database server is running and accessible. Check your network connection and verify the correctness of your credentials. Challenge 3. Explain in detail data format issues. The data stored in Astra DB might not be in a Format suitable for Langchain document processing. Sample use case that resulted in challenge 3. If the document content in Astra DB is stored as a single string without clear delimiters between documents, the loader might not be able to properly extract individual documents. Fixes to challenge 3. Pre-process the data in Astra DB to ensure it is formatted in a way that the loader can handle, such as separating documents with clear delimiters. Langchain Astra DB storage. Description. Explain in detail. The Langchain Astra DB storage component enables persistent storage and retrieval of data within Langchain applications using data stacks. Astra DB, a fully managed cloud database service built on Apache Cassandra. Inputs. Input 1. Explain in detail. This component requires a connection to your Astra DB database instance. This is typically achieved by providing credentials, such as the database name, key space, and authentication details. Input 2. Explain in detail the data to be stored. This can be any type of data that you need to persist, such as text, embeddings, or other structured information. This will depend on how you are using the storage component. Outputs. Output 1. Explain in detail the stored data. This allows you to retrieve the data later for use in your Langchain application. Output 2. Explain in detail metadata about the stored data. This can be useful for tracking and managing the data within your application. Steps. Step 1. Explain in detail. Establish a connection to your Astra DB database instance using the provided credentials. Step 2. Explain in detail. Insert the provided data into the database, potentially using a specific table or collection based on your application's needs. Metrics. Metric 1. Explain in detail. Storage size tracks the amount of data stored in the database. This can be monitored over time to gauge usage patterns and potential optimization needs. Metric 2. Explain in detail. Query performance measures the latency of read and write operations against the database. This can help identify bottlenecks and inform strategies to improve application responsiveness. Visualization plots. Visualization plot 1. Explain in detail storage size over time. This can be visualized as a line chart to show how the amount of data stored in the database evolves over time. Visualization plot 2. Explain in detail query performance distribution. A histogram showing the frequency of query latency values can help to understand the typical performance of read and write operations. Fine-tune parameters. Parameter 1. Explain in detail key space. This parameter allows you to specify the key space within your Astra DB database where data should be stored. It helps to organize and structure your database. Parameter 2. Explain in detail table name. This parameter allows you to specify the specific table or collection within your key space where the data should be stored. Uncertainty methods. Uncertainty method 1. Explain in detail. Not directly applicable. This component primarily focuses on deterministic storage and retrieval of data, not on inferential or probabilistic tasks. Uncertainty method 2. Explain in detail. Not directly applicable. See Uncertainty method 1 explanation. Challenges and fixes. Challenge 1. Explain in detail connection errors. This can occur if there are issues with the provided credentials, network connectivity, or if the database is unavailable. Sample use case that resulted in challenge 1. Attempting to connect to the database using incorrect credentials or while the database is experiencing downtime. Fixes to challenge 1. Verify the provided credentials, ensure network connectivity, and check the status of the Astra DB instance. Challenge 2. Explain in detail data consistency issues. There is a possibility of data inconsistency if the database experiences a failure or interruption during a write operation. Sample use case that resulted in challenge 2. A network outage occurs during a large data write operation, causing a partial write and leading to inconsistencies. Fixes to challenge 2 utilize Astra DB's built-in consistency features and mechanisms, such as write consistency levels, to ensure data integrity. Additionally, consider implementing retry logic in your application to handle potential write failures. Langchain Astra DB Storage Astra DB Byte Store. Description: The Astra DB Byte Store class is a Langchain storage implementation that utilizes the Astra DB database to store and retrieve bytes. This allows you to store and retrieve arbitrary data such as images, audio files, or other binary data. Inputs: Astra DB client, an instance of the Astra DB client to connect to the Astra DB database. This client is responsible for handling communication with the database. Table name: the name of the Astra DB table where the data will be stored. This table should be created beforehand, and it's recommended to have a structure suitable for storing binary data, e.g., a key column and a data column. Outputs: stored bytes. The Astra DB Byte Store class stores bytes in the specified Astra DB table, associating them with a unique key. Retrieved bytes: when you provide a key, the Astra DB Byte Store class retrieves the corresponding bytes from the specified table. Steps: initialization: the Astra DB Byte Store is initialized with the Astra DB client and the table name. This sets up the necessary connection to the database. Storage: to store bytes, you call the save method, providing a unique key and the bytes to be stored. The store then inserts this data into the specified Astra DB table. Retrieval: to retrieve stored bytes, you call the load method with the key associated with the stored bytes. The store then retrieves the data from the table based on the key and returns the bytes. Metrics: storage time: this metric measures the time it takes to store bytes in the Astra DB database. It can be helpful to assess performance and identify potential bottlenecks. Retrieval time: this metric measures the time it takes to retrieve bytes from the Astra DB database. Similar to storage time, this metric can be used to evaluate performance and identify areas for optimization. Visualization plots: performance graph: a graph visualizing the storage and retrieval times over a period, which helps to understand trends in performance and identify potential issues. Data size distribution: a visualization showing the distribution of stored data sizes, which can be helpful to analyze how the storage space is utilized. Fine-tune parameters: table name: choosing the correct table name allows for organized storage and efficient retrieval. Data compression: if applicable, implementing data compression can significantly reduce storage space requirements. Indexing: adding appropriate indexes can speed up retrieval of data by efficiently searching through the Astra DB table. Uncertainty methods: no specific uncertainty methods apply to this class, as it focuses on deterministic storage and retrieval of data. Challenges and fixes: Challenge 1: performance issues, slow storage or retrieval times can be encountered, especially when dealing with large datasets. Sample use case that resulted in challenge 1: attempting to store or retrieve large images or videos might lead to performance bottlenecks. Fixes to challenge 1: optimize database queries, analyze and refine the queries used for storing and retrieving data to reduce query execution times. Utilize data compression, employ compression algorithms to reduce data size, potentially leading to faster storage and retrieval. Consider indexing, adding appropriate indexes can significantly speed up retrieval of specific data based on certain criteria. Challenge 2. Data integrity. Data corruption or loss during storage or retrieval can occur due to various factors. Sample use case that resulted in challenge 2. Network interruptions or database issues might lead to data loss or inconsistencies. Fixes to challenge 2. Implement error handling. Incorporate robust error handling mechanisms to detect and recover from potential failures during storage or retrieval. Use transaction isolation. Utilize database transactions to ensure data consistency and prevent partial updates in case of interruptions. Regularly backup data. Implement regular backups of the data stored in Astra DB to protect against accidental data loss or corruption. Langchain Astra DB Storage. Astra DB Store. Description: the Astra DB Store class is a Langchain storage component designed to interact with data stacks Astra DB. It allows you to store and retrieve data in your Astra DB database from your Langchain applications. This class leverages the Astra DB Python driver for efficient database interactions. Inputs: Astra DB client, an instance of the data stack's Astra DB Python driver, providing the necessary connection parameters to the Astra DB database. Table name: the name of the table within the Astra DB database where data will be stored when retrieved. Primary key name: the name of the primary key column in the Astra DB table. This column will uniquely identify each record within the table. Outputs: data retrieved from the Astra DB table based on provided keys. Stored data in the Astra DB table. Steps: establish a connection to the Astra DB database using the provided Astra DB client instance. Utilize the provided table name to specify the target table for data operations. Use the primary key name to identify and access specific records within the table. Metrics: latency: measure the time taken to execute read and write operations on the Astra DB database. Throughput: evaluate the rate at which data can be stored and retrieved from the Astra DB database. Visualization plots: data visualization plots can be generated using libraries like matplotlib or seaborn to represent the data stored in the Astra DB table. This can be helpful in understanding data trends and patterns. Performance visualization plots can be generated to depict latency and throughput metrics over time, providing insights into the performance of the Astra DB store. Fine-tune parameters: Astra DB client: modify the configuration parameters of the Astra DB client to adjust connection settings, such as the Astra DB database URL, authentication credentials, and database key space. Table name: specify a different table name within the Astra DB database to store and retrieve data from a different table. Uncertainty methods: data integrity: the Astra DB store relies on the data integrity and consistency guarantees provided by Astra DB. This can be evaluated through various methods, such as comparing the data stored in the database with the data retrieved from the storage component. Challenges and fixes: Challenge 1: incorrect configuration of the Astra DB client instance, including invalid connection parameters or missing authentication credentials. Sample use case: a user attempts to connect to the Astra DB database using an incorrect database URL or a missing authentication token. Fixes: review and correct the configuration parameters of the Astra DB client instance, ensuring the database URL, authentication credentials, and other settings are valid and correctly specified. Challenge 2. Unclear or incorrect usage of the table name or primary key name, leading to data access errors. Sample use case: a user attempts to retrieve data from a table using a non-existent table name or an incorrect primary key value. Fixes: verify the correctness of the table name and primary key name values. Ensure that the provided table name exists in the Astra DB database and that the primary key value corresponds to a valid record in the table. Challenge 3. Network connectivity issues or temporary outages in the Astra DB service, leading to read or write failures. Sample use case: a user attempts to store data in the Astra DB database while experiencing network connectivity problems or a temporary disruption in the Astra DB service. Fixes: implement error handling mechanisms in the application code to gracefully manage potential network connectivity issues or temporary outages in the Astra DB service. This might involve retrying operations or using mechanisms like exponential backoff to handle transient errors. Challenge 4. Data inconsistency issues, particularly when multiple concurrent operations are performed on the Astra DB database. Sample use case: multiple users attempt to access and modify the same data in the Astra DB database simultaneously. Fixes: utilize the features provided by Astra DB, such as optimistic concurrency control, to address data consistency issues in concurrent scenarios. Langchain Astra DB Utils. Description: the Langchain Astra DB Utils provide a convenient way to interact with Astra DB. A fully managed, serverless database as a service from within Langchain. This allows developers to seamlessly integrate Astra DB into their Langchain applications, enabling data-driven LLM applications that leverage the power of Astra DB's capabilities. Inputs. Connection parameters: the utils require connection parameters to establish a connection to Astra DB, including the Astra DB database URL, key space name, and authentication credentials. Query: a SQL query that will be executed against Astra DB. This query can be a simple select statement, an insert query, or any other valid SQL command. Data: for tasks like inserting or updating data, you provide the data to be processed by the query. Langchain components: the utils can be used with various Langchain components, such as chains, prompts, and tools, making it easy to integrate Astra DB into your existing Langchain workflows. Outputs. Query results: the utils return the results of the executed SQL query, typically as a list of dictionaries or a pandas data frame. Data transformation: if the query is an update or insert, the utils can return information about the affected data. Errors: if there are errors during the connection establishment, query execution, or data processing, the utils will raise appropriate exceptions. Steps. Establish connection: the utils first connect to the Astra DB instance using the provided connection parameters. This step involves authentication and authorization using the supplied credentials. Execute query: once connected, the utils execute the provided SQL query against the specified database. This involves parsing the query and sending it to Astra DB for processing. Process results: the utils then retrieve and process the results returned from Astra DB. This might involve formatting the data into a suitable format, such as a list of dictionaries or a pandas data frame, depending on the query and user requirements. Metrics. Query execution time: the utils can measure the time taken to execute the SQL query against Astra DB. This helps assess query performance and identify potential bottlenecks. Data processing time: the time spent processing the query results. including formatting and transformations, can be tracked to understand the overhead involved. Connection latency: the time taken to establish a connection with Astra DB can be measured to evaluate the overall network latency. Visualization plots. Query execution timeline: a visual representation of the time taken to execute the query, including connection establishment, query processing, and data retrieval. Data distribution plots showing the distribution of data in the results, such as histograms for numerical values or bar charts for categorical data. Fine-tune parameters. Query optimization: the utils can leverage Astra DB's query optimization features to improve efficiency of SQL queries, potentially resulting in faster execution times. Data caching: the utils can cache query results to avoid redundant database calls for frequently accessed data, reducing latency and improving performance. Connection pooling: for applications with high concurrency, the utils can implement connection pooling to manage multiple connections efficiently, reducing the overhead of establishing new connections. Uncertainty methods. Data integrity validation: the utils can perform validation checks on the data retrieved from Astra DB to ensure data integrity and consistency, reducing the risk of errors in downstream applications. Error handling: the utils can implement robust error handling mechanisms to capture and handle exceptions during query execution or data processing, ensuring application stability and resilience. Challenges and fixes. Challenge 1: authentication errors. Sample use case that resulted in challenge 1: an incorrect Astra DB database URL, keyspace name, or authentication credentials were provided. Fixes to challenge 1: double-check the connection parameters, including the database URL, keyspace name, and authentication credentials. Ensure that the credentials have the necessary permissions to access the database. Challenge 2: query execution errors. Sample use case that resulted in challenge 2: an invalid SQL query was provided, resulting in a syntax error or other database errors. Fixes to challenge 2: carefully review the SQL query for syntax errors. Ensure that the table and column names are correct, and validate the query structure against the database schema. Challenge 3: data retrieval errors. Sample use case that resulted in challenge 3: data retrieval failed due to network issues, database connectivity problems, or permissions restrictions. Fixes to challenge 3: check network connectivity and ensure that the Astra DB instance is accessible. Verify that the provided credentials have the necessary read permissions for the target data. Challenge 4: data transformation errors. Sample use case that resulted in challenge 4: an error occurred during the conversion or processing of the query results, such as formatting issues or type mismatch. Fixes to challenge 4: review the data transformation logic and ensure that the data types and format are compatible. Consider using data validation techniques to identify and address potential inconsistencies. Challenge 5: error handling. Sample use case that resulted in challenge 5: the utils did not properly handle exceptions or errors during the connection, query execution, or data processing steps, potentially leading to application crashes. Fixes to challenge 5: implement robust error handling mechanisms using try-except blocks. Capture and log errors to identify and address potential issues. Provide appropriate error messages to users or applications. Langchain Astra DB utils Astra DB setup mode. Description: the setup mode enum in Langchain Astra DB utils Astra DB defines the different ways you can set up your Astra DB database connection for Langchain. This enum impacts how the database is initialized and how your Langchain applications interact with it. Inputs. Database credentials. This includes your Astra DB database name, region, keyspace name, and authentication credentials, usually your Astra DB token. Database schema. This refers to the structure of your database, including tables, columns, and relationships. You can choose to create a new database schema, use an existing one, or provide a configuration file to define the schema. Outputs. Database connection. A connection object that allows your Langchain applications to interact with the Astra DB database. Database schema. If created, the created database schema, including table definitions and relationships. Steps. Database initialization. Depending on the selected setup mode, the library will attempt to connect to your Astra DB database and either initialize a new database, create a new keyspace, or connect to an existing one. Schema creation verification. If you are creating a new database or keyspace, the library will apply the provided database schema to create the necessary tables and columns. If you are connecting to an existing database, the library will verify that the specified tables and columns exist. Connection establishment. The library will establish a connection to your Astra DB database using the provided credentials and database information. Metrics. Connection time. The time it takes to establish a connection to the Astra DB database. Schema creation verification time. The time taken to create or verify the database schema. Database query performance. The speed and efficiency of queries executed against the Astra DB database. Visualization plots. Database schema visualization. A diagram that represents the structure of your database, including tables, columns, and relationships. Query execution time. Histogram. A histogram that shows the distribution of query execution times for your database. Fine-tune parameters. Astra DB token. Your Astra DB token for authentication. Database name. The name of your Astra DB database. Keyspace name. The name of your keyspace within the database. Region. The region where your Astra DB database is located. Setup mode. The selected setup mode for initializing the database connection. Uncertainty methods. This is related to model prediction, not database setup. Challenges and fixes. Challenge 1. Incorrect or invalid database credentials. Sample use case. You might have entered a wrong database name, keyspace name, or provided an expired Astra DB token. Fixes. Double-check all credentials. Ensure you have a valid Astra DB token, and confirm the database name and keyspace name are correct. Challenge 2. Schema creation issues. Sample use case. You might encounter errors when creating the database schema due to conflicting table names, column types, or data validation constraints. Fixes. Review your database schema for inconsistencies or errors. Make sure the column types match the data you plan to store. Check for duplicate table or column names. Challenge 3. Network connectivity issues. Sample use case. You might be unable to connect to Astra DB due to network connectivity problems, firewall restrictions, or server outages. Fixes. Verify your network connectivity. Ensure any necessary firewalls are allowing access to Astra DB, and check the status of the Astra DB servers. Challenge 4. Database capacity limits. Sample use case. You might encounter errors if you attempt to create a database that exceeds the available storage or compute resources for your Astra DB account. Fixes. Check your Astra DB account limits for storage and compute resources. If necessary, upgrade your account or optimize your database schema to reduce storage requirements. Langchain Astra DB utils MMR cosine similarity. Description: this utility function calculates the cosine similarity between two vectors, which are typically representations of text documents. It leverages the MMR maximal marginal relevance algorithm to select the most relevant and diverse documents. Inputs. Query: the input query or text prompt that the user provides. Documents: a list of documents that have been embedded into vector representations. Outputs. Scores: a list of cosine similarity scores between the query and each document. Ranked documents: a list of documents ranked by their cosine similarity scores with the query. Steps. Embed the query using the same embedding model used to embed the documents. Calculate the cosine similarity between the query embedding and each document embedding. Utilize the MMR algorithm to select the most relevant and diverse documents based on their cosine similarity scores and their similarity to previously selected documents. Metrics. Cosine similarity measures the similarity between the query and document embeddings. MMR score measures the relevance and diversity of the selected documents. Visualization plots. Scatter plot visualizes the cosine similarity scores between the query and each document. Rank plot visualizes the ranking of documents based on their cosine similarity scores. Fine-tune parameters. MMR lambda controls the trade-off between relevance and diversity in the MMR algorithm. Uncertainty methods. Confidence intervals provides a range of possible values for the cosine similarity scores, indicating the uncertainty in the model's predictions. Challenges and fixes. Challenge 1: the MMR algorithm might struggle to select diverse documents when the documents are highly similar to each other. Sample use case that resulted in challenge 1: a set of documents about a specific topic, where all documents contain similar information and vocabulary. Fixes to challenge 1: increase the value of the MMR lambda parameter to prioritize diversity over relevance. Challenge 2: the cosine similarity metric might be insensitive to subtle differences in meaning between documents, resulting in inaccurate rankings. Sample use case that resulted in challenge 2: documents with similar keywords but different semantic meanings. Fixes to challenge 2: consider using a more advanced similarity metric like sentence BERT SBERT or a semantic search algorithm that accounts for word embeddings and semantic relationships. Langchain Astra DB utils MMR maximal marginal relevance. Description: the maximal marginal relevance MMR algorithm is a technique used to select a set of documents or sentences that are both relevant to a query and diverse from each other. This helps to ensure that the returned results are comprehensive and provide a varied perspective. The algorithm balances relevance and diversity by considering both the similarity of a document to the query relevance and the similarity of a document to previously selected documents' diversity. Inputs. Query: the user's search query or topic of interest. Documents: a set of documents or sentences that are potential candidates for selection. Outputs. Selected documents: a ranked list of documents that are both relevant and diverse. Steps. Initialization: the algorithm begins by selecting the document most relevant to the query. Iteration: in each subsequent iteration, the algorithm considers all remaining documents and calculates a score for each document. This score is a weighted combination of the document's relevance to the query and its dissimilarity to the already selected documents. Selection: the document with the highest score is selected and added to the set of selected documents. Metrics. Recall the proportion of relevant documents that are retrieved. Precision, the proportion of retrieved documents that are relevant. Diversity, a measure of the difference between the selected documents. Visualization plots. Scatter plot showing the relevance and diversity scores of each document. Heat map visualizing the similarity between selected documents. Fine-tune parameters. Lambda, a parameter that controls the trade-off between relevance and diversity. A higher value of lambda favors diversity, while a lower value favors relevance. Uncertainty methods. Confidence scores. The model can output confidence scores for each selected document, indicating the level of certainty in its relevance and diversity. Challenges and fixes. Challenge 1. The MMR algorithm can be computationally expensive, especially when dealing with large document sets. Sample use case that resulted in challenge 1: selecting documents from a large corpus of text for a complex query. Fixes to challenge 1. Optimize the similarity calculations by using efficient indexing techniques. Use approximate nearest neighbor search and algorithms to speed up the process. Consider using a smaller subset of documents for initial selection. Challenge 2. The MMR algorithm can struggle to select diverse documents if the query is very specific. Sample use case that resulted in challenge 2: selecting documents about a specific technical topic, where most documents are highly similar. Fixes to challenge 2. Increase the value of lambda to prioritize diversity. Pre-process the documents to identify clusters of similar documents and select representatives from each cluster. Consider using a different diversity measure that is more sensitive to the specific domain. Challenge 3. The MMR algorithm can be sensitive to the choice of similarity measure. Sample use case that resulted in challenge 3: selecting documents using a similarity measure that does not capture the semantic relationships between documents. Fixes to challenge 3. Experiment with different similarity measures to find one that is appropriate for the task. Consider using embedding models to represent documents in a semantic space. Use a hybrid approach that combines multiple similarity measures. Langchain Astra DB Vector Stores. Description: the Langchain Astra DB Vector Store is a specialized vector database designed to efficiently store and retrieve vector embeddings, making it ideal for use in various language-based tasks such as semantic search, question answering, and document summarization. It leverages the capabilities of Astra DB, a scalable and fully managed database as a service platform, to provide a robust and highly performant solution for vector data management. Inputs. Documents. This input represents the collection of text documents that will be converted into vector embeddings. These documents can be in various formats like plain text, Markdown, or HTML, and can contain textual content such as articles, books, code, or any other textual information relevant to the application. Embeddings. Vector embeddings are numerical representations of the input documents, capturing their semantic meaning. These embeddings are generated by embedding models, such as OpenAI's Ada, Babbage, Curie, and DaVinci models, which learn to map text to vectors in a way that captures semantic similarity. Outputs. Vector database. The vector database stores the generated vector embeddings along with their associated document IDs and metadata. This database is optimized for efficient retrieval of vectors based on their similarity, enabling rapid search and retrieval of relevant documents based on semantic meaning. Search results. When a query is submitted, the vector store performs a similarity search using the query's embedding. It returns a ranked list of documents with the most similar documents appearing at the top. These search results provide a semantic understanding of the query and identify the most relevant documents based on their contextual similarity. Steps. Embedding generation. The input documents are first passed through an embedding model to generate vector embeddings for each document. This process converts text into numerical representations, capturing the semantic meaning of the documents. Vector database storage. The generated vector embeddings, along with their associated document IDs and metadata, are then stored in the Astra DB vector database. This database is specifically designed to handle vector data efficiently, providing optimized indexing and search capabilities. Query embedding in search. When a query is submitted, it is also embedded into a vector representation using the same embedding model. This query embedding is then used to perform a similarity search within the vector database, comparing it to the stored embeddings. Result ranking and retrieval. The search results are ranked based on their similarity to the query embedding, with the most similar documents appearing at the top. The relevant documents are then retrieved from the vector database, providing a semantically relevant response to the query. Metrics. Accuracy. This metric measures the effectiveness of the vector database in retrieving relevant documents based on semantic similarity. It assesses the percentage of correct matches in the search results compared to the expected results. Retrieval time. This metric measures the speed and efficiency of the search process within a vector database. It reflects the time taken to retrieve relevant documents from the database based on a given query. Storage capacity. This metric indicates the total amount of data that can be stored in the vector database. It reflects the ability of the database to accommodate large datasets of vector embeddings and associated metadata. Visualization plots. Similarity matrix. This visualization displays the pairwise similarity scores between the vector embeddings in the database. It provides a visual representation of the semantic relationships between documents and helps identify clusters of similar content. Search results distribution. This plot shows the distribution of search results across different document categories or topics. It helps visualize the effectiveness of the vector database in retrieving relevant documents from different thematic areas. Fine-tune parameters. Embedding model. The choice of embedding model plays a crucial role in determining the accuracy and efficiency of the vector database. Different embedding models offer varying levels of accuracy and performance, depending on the specific use case. Similarity metric. The similarity metric used for comparing query embeddings to the stored embeddings influences the search results. Common metrics include cosine similarity, Euclidean distance, and Manhattan distance. Uncertainty methods. Confidence scores. These scores provide an estimate of the uncertainty associated with each search result. They indicate the degree of confidence in the retrieved documents based on their similarity to the query embedding. Multiple embeddings. Generating multiple embeddings for each document using different embedding models can provide a more robust representation and reduce uncertainty. Challenges and fixes. Challenge 1. High dimensionality of embeddings. Vector embeddings often have a high number of dimensions, making it computationally expensive to store and perform similarity searches. Sample use case that resulted in Challenge 1: a large dataset of articles with complex semantic relationships, leading to high-dimensional vector embeddings. Fixes to Challenge 1: dimensionality reduction techniques. Apply techniques like principal component analysis (PCA) or TSNA to reduce the number of dimensions while preserving the most important information. approximate nearest neighbor search and use approximate algorithms like FICE, ANOI, or HNSW for fast similarity searches in high-dimensional spaces. Challenge 2: Scalability: handling large datasets of vector embeddings and managing the growing size of the database can be challenging. Sample use case that resulted in challenge 2: a continuously expanding knowledge base with millions of documents, leading to a significant increase in the size of the vector database. Fixes to challenge 2: utilize a scalable database. Leverage the capabilities of a distributed database like Astra DB, which can handle large volumes of data efficiently and distribute processing across multiple nodes. Data partitioning and sharding: partition the data into smaller chunks and distribute them across multiple servers for parallel processing and storage. Implement caching mechanisms: use caching techniques to store frequently accessed data in memory for faster retrieval and reduce database load. Langchain Astra DB Vector Stores. Astra DB Vector Store. Description: the Astra DB Vector Store is a Langchain vector store that uses Astra DB as its backend. It allows you to store and retrieve embeddings in a scalable, reliable, and cost-effective manner. Astra DB's managed cloud database infrastructure handles data storage, while Langchain's integration makes it easy to interact with the database from your Python code. Inputs: connection config: a dictionary containing the connection configuration information for your Astra DB database. This includes details like database name, key space, and authentication credentials. Embedding function: an embedding function that takes a text input and returns a vector representation of the text. This could be a pre-trained embedding model from Hugging Face or a custom embedding function. Outputs: a Langchain vector store instance that can be used to store, retrieve, and search embeddings. This instance allows you to perform operations such as adding new embeddings, finding similar embeddings, and querying the database using vector search. Steps: initialization: the Astra DB vector store is initialized with the connection configuration and pay embedding function. Embedding generation: the vector store uses the embedding function to generate embeddings for pay input texts. Data storage: embeddings and their associated metadata are stored in Astra DB. Astra DB's document-based structure allows you to store the embeddings along with additional information such as document titles, URLs, or other relevant data. Vector search: the Astra DB vector store leverages Astra DB's native vector search capabilities to efficiently find similar embeddings within the database. Metrics: embedding similarity: the quality of the embeddings can be assessed using metrics like cosine similarity or Euclidean distance. Retrieval accuracy: the accuracy of the vector search algorithm can be measured by evaluating how well it retrieves relevant documents based on the query embedding. Query latency: the time taken to perform a vector search query can be measured to evaluate the performance of the system. Visualization plots: embedding visualization scatter plots or other visualization techniques can be used to visualize the embedding space and understand the relationships between different embeddings. Search results visualization: visualization can be used to represent the results of a search query, highlighting the similarity scores between the query embedding and the retrieved embeddings. Fine-tune parameters: embedding model: you can experiment with different pre-trained embedding models to find the one that best suits your data and task. Vector search algorithm: Astra DB supports various vector search algorithms. You can choose the algorithm that provides the best balance between accuracy and performance for your needs. Index configuration. The configuration of the vector search index in Astra DB can be tuned to optimize the performance of the search. Uncertainty methods. Similarity threshold. You can set a similarity threshold to filter out results that are below a certain level of similarity to the query. Ranking. The search results can be ranked based on similarity scores, providing a measure of confidence in the retrieved embeddings. Challenges and fixes. Challenge 1. High latency during vector search queries. Sample use case that resulted in challenge 1. Large datasets with complex embedding models can lead to increased query latency. Fixes to challenge 1. Optimize the Astra DB index configuration by adjusting parameters like the number of segments and the indexing strategy. Consider using a more efficient embedding model that generates smaller and faster to search embeddings. Explore caching mechanisms to reduce the number of database queries for repeated searches. Challenge 2. Limited support for certain embedding models. Sample use case that resulted in challenge 2. Some embedding models may not be directly supported by the Astra DB vector search engine. Fixes to challenge 2. Explore third-party integrations or custom embedding functions that can bridge the gap between the embedding model and Astra DB's search capabilities. Consider alternative vector search engines that have wider support for embedding models. Challenge 3. Handling data updates and deletions. Sample use case that resulted in challenge 3. When the data in the database is updated or deleted, the vector store needs to reflect these changes. Fixes to challenge 3. Implement mechanisms to track data updates and deletions. Update the vector search index accordingly to ensure that search results reflect the latest data.